Hey, y'all. We're going to talk about the next concept in thermodynamics. And the concept is called Hess's law. But the idea is that each step in a reaction either releases energy or consumes energy. It's either exothermic, the system giving off energy, or it's endothermic, the system taking in or absorbing energy, right? So we're going to look at how these reactions work, what kind of things take in energy, what kind of things give off energy. And we're also going to look at how when you put these different components of a reaction together, you can get an enthalpy or an energy change, a heat under constant pressure change for the reaction overall. So if you look on this slide, what I have here is the same reaction in one step versus the reaction broken up into multiple steps. So here you can see a one-step reaction. Now, these are the types of reactions that we typically talk about in like our first year of high school chemistry, right? We give you two reactants, nitrogen and oxygen, and they react to form nitrogen dioxide, right? So we have an overall enthalpy change for this reaction. Notice the enthalpy change is positive, which means this reaction energy or heat is going to flow into the system, the atoms, and the molecules. So it's an endothermic reaction. Now we can look at that same reaction in a multi-step process. Now, reactions don't usually just happen in one step, right? We don't just smush it together, voila, we get it out. Same thing with like baking cupcakes, right? We don't just have all the ingredients and then we smush them together and voila, we have cupcakes, right? We have to break the eggs. That's going to take energy to break the eggs. We have to mix them all together in a specific order. That's going to take energy. We have to put it into the oven for a specific amount of time and at a specific temperature. Energy is going to go from the oven into our system. So the act of baking cookies really isn't a one-step process. And it's the same for lots of reactions as well. The actual reaction is broken up into these various steps that all come with their energy changes, right? All of these various steps are going to give off or take in energy. So that's what you can see down below. Notice here I have my two molecules, my two reactants, and they're actually forming NO. Nitrogen monoxide, not NO2 like I have above. They're forming this intermediate that doesn't show up as a reactant or a product, right? And then NO in turn is going to react with oxygen and form NO2. So it's a multi-step process similar to like a recipe for baking would be. In the end, these two steps are going to come together to give me an overall reaction. And notice that overall reaction is the same as the overall reaction in my one-step process. Likewise, the energies for these steps are going to come together and give off an overall enthalpy change for the reaction, which is the same as the enthalpy change in the first step was. Now, I want to take just a little bit of time and talk about how those two reactions combine to form the overall reaction, just so you see this. Okay, so when we're adding reactions together, basically you're going to look at the reactants and you're going to look at the products, right? Okay, so in our reactants, I have nitrogen, N2. I have two oxygens, and I have this mysterious nitrogen monoxide. Okay, now on the product side, let me do that in another color so it's very obvious. On the product side, I have two nitrogen monoxides and I have two nitrogen dioxides. Okay, so if I have something in the beginning and I have something in the end. If we were talking about a net ionic reaction, we would call this a spectator, right? It kind of floats around and it doesn't actually do anything. Well, in this case, it's not actually a spectator. It does get formed, but then it also gets consumed. And so in an overall reaction, we are not going to include it just like a spectator, even though it does do something. It gets formed and then it gets consumed. So we would call this an intermediate. So conceptually, it's a little bit different than a spectator. But functionally, in our equation, we're going to treat it exactly like we treat it as a spectator. If it's there in the reactants, it's there at the products, it gets X'd out. It's not in our net ionic equation. And then I have this overall reaction, which is the same as my overall reaction in the one step. Now, why would I want to break it up into multiple steps? Good question. There's a variety of reasons. Maybe you want to control how fast it happens and you need to control the intermediate or support the intermediate's formation in order to do that. Maybe you want to know exactly how this happens so that you know why you put in energy and where you get out energy. There's a bunch of different reasons you might want to break it down. There's probably an equal amount of reasons you wouldn't want to know about the intermediate, right? But sometimes it's really convenient. Sometimes we can't actually calculate an overall enthalpy reaction, but we can calculate the enthalpy changes for the step 1 and step 2, and then we can use those in order to figure out an overall enthalpy change. Notice that we take 180 and we add it to a negative 112 to get our overall reaction, right? So I can show this to you in another way. Let me show you the exact same concept here, only in a graph. So notice I have a graph. It's an energy graph, right? So I have enthalpy on this side. This up here would be high. At the bottom here, it would be low. And then notice you have your reactants here. And then this arrow, this first blue arrow right here, tells you it's a change of 180 kilojoules. And it brings you that when you input 180 kilojoules, it brings you to your first set of intermediates or products on that first reaction, right? Nitrogen monoxide and oxygen. So we have to input 180 kilojoules in order to get there. So basically what happens is we are taking that nitrogen, it's actually a triple bond if you look at the Lewis dot diagram, and we are breaking that bond. And then you're also taking one of the oxygens. Notice you have 2 oxygen molecules listed here. So you're taking one of the oxygens and breaking those bonds as well. And then those 2 molecules reform. The nitrogen attaches to the oxygen. This nitrogen attaches to the oxygen. So we get 2 of these NO molecules, and then we have 1 of the oxygens left over. And then you start on the second step. You start there, and you end with nitrogen dioxide. So what happens there must be that oxygen that's remaining also gets broken. And then each of these oxygens gets attached to a nitrogen monoxide molecule to form nitrogen dioxide there. And that breaking of the oxygen bond and then that formation of that new oxygen-nitrogen bond is actually going to give off 112 kilojoules. And so our net change here is from the bottom to this top. This net change here is going to be 68 kilojoules. And you see you get it from adding these other 2 together. On the other hand, we can graphically display this as a one-step reaction. You would have reactants and products, and then you would have this net input of 68 kilojoules of energy. Okay, so we can do this, we can represent this through symbols and numbers, we can represent this graphically, but they both kind of tell the other story. And so this is the idea behind Hess's law, that you can take certain reactions and add them together to get this one net reaction. Now, this is really convenient because some reactions are a lot easier to measure the enthalpy change for than other reactions. So if you're dealing with a reaction that's really tough to measure the enthalpy change for that reaction, well, you can look at a variety of other reactions that maybe they already have the enthalpy change measured, or maybe they're a lot easier to measure, and you can actually build your final reaction from these others. Now, let me show you something in your book while we're talking about this. If you go to the back of your book, there is an appendix starting, let's see. It's in front of the given answers, and it's an appendix that actually lists a whole bunch of these enthalpy changes. You might want to get a sticky note so you can actually mark this. So on my book, it says it's on page A21. So A is for the appendix and 21 is page 21 of the appendix. And so you'll get a chart that looks like this. It says thermodynamic data. And notice there's delta H, not F, is listed in kilojoules per mole. Right there. And it's got a lot of compounds listed next to it. Now, we're going to talk about what this means in the next couple days. But before we do that, I want you to walk through a couple exercises that will help you kind of wrap your brain around this concept of enthalpy and enthalpy change in certain reactions. Now, before you do this, there's a couple things I want you to keep in mind. Thing number one is, remember how we talked in the beginning about how the subscript is really important, right? Delta H subscript. That subscript can be a whole bunch of things. That subscript can be reaction. That subscript can be neutralization. That subscript can be combustion. That subscript can be formation. You're going to see one for AC in one of these activities, which is atom combination. So that tells you what is going on, what kind of reaction you're dealing with. So if you see like a delta H, like in that table, you see a delta H not. Remember that not either specifies that it's initial or it specifies certain conditions like standard conditions, STP, standard temperature and pressure, right? And then you have the subscript. So if you have delta H naught combustion listed for, I don't know, let's say CH4, and it gives you a value of negative 400 kilojoules. I'm totally making this up, but let's roll with it. Okay, so this is all the information they give you. They don't give you a reaction. This enthalpy change is for the reaction. It's for the combustion reaction of methane. So they don't give you the reaction because they assume you can write it. So take 30 seconds, pause the video. Can you write me the combustion reaction for CH4? All right, there you go. That's the combustion reaction for methane. So the enthalpy of combustion for methane that they give you, which I made up the number, I'm pretending that it's negative 400 kilojoules per mole. Okay, so that is for the reaction that we just wrote. So sometimes they don't give you the reaction because they expect you can write it yourself. Also, note that it's usually per mole, or they give you that naught symbol. That means it's standard conditions. Standard conditions includes 1 mole. So you have to be really careful to write your equation in terms of 1 mole of the compound that they give you. And sometimes you might have to use fractions as your coefficients in order to balance this equation so that it comes out to be 1 mole of the compound that you're looking at. Okay. Formation. Let me just talk to you about this now, and then we can talk about it later. The whole chart in your book is listed in terms of formation reaction. So they'll give you the enthalpy. Let me delete what I have on the board for a second. They'll give you enthalpy F. F stands for formation for a specific molecule. And so let's use CH4 again, okay? So a formation reaction is always going to be from elements to the compound that you're looking at. So when you write a formation reaction, it must be from elements to the molecule that you're looking at, okay? So here's where memorizing your diatomics is going to pay off, because you have to know the elemental form of things. Look at CH4, for example. If we're going to write the formation reaction for CH4 from elements to methane, we're going to use elemental carbon, which is C, and elemental hydrogen. Now, elemental hydrogen is not H. That's atomic hydrogen. Elemental hydrogen is H2. It's one of your 7 diatomics. And if your element that you're using is a diatomic, you must use the molecule, the diatomic molecule, not the atomic form. Okay, so we have our element of carbon, we have our element of hydrogen. It's going to form our molecule that we want, and then we need to balance it because it's standard conditions, right? We need to balance it so that it's 1 mole of CH4. In this case, it's fairly easy to do. We just double the hydrogen. But again, you might have to use fractions in order to get the reaction to balance out to 1 mole of CH4. Let me give you an example of that. How about the formation of carbon monoxide? Okay, pause it here. See if you can write the formation reaction for carbon monoxide. Okay, elemental carbon, C, elemental oxygen is O2. Now I'm going to form carbon monoxide, CO, but I don't want to double my carbon monoxide and double my carbon, because that will give me more than 1 mole of the thing that I'm looking for, which is carbon monoxide. And I want to balance this so that I come out with 1 mole of carbon monoxide. So at this point in time, you can just do what I just did. You can just balance it like you normally would. But at this point in time, you need to divide by this coefficient. You need to divide everything by this coefficient. So I'm going to divide carbon monoxide by 2, I'm going to divide the coefficient of oxygen by 2, and I'm going to divide the coefficient of carbon by 2. So my reaction comes out to be C plus a half of oxygen gives me 1 mole of carbon monoxide. There you go. So the enthalpy, the delta H naught F for carbon monoxide listed in your book, is actually the amount, the enthalpy change for this reaction overall. So you have to be really careful of the subscripts, because they don't always give you a reaction. They're assuming you can write a reaction for the subscript. So what do you think the delta H naught F for, actually, let me delete this. Well, I'll write it on this other side. What would you suspect the delta H naught F would be for something like O2? Pause it for just a second and think about your answer there. So O2 is an element, right? If we form molecular oxygen from elemental oxygen, which is O2, our reaction would look like this. O2 goes to O2, right? Which means no reaction has occurred. No change, no chemical change occurred there. no reaction happens. So the delta H naught F for any element is going to be 0 because it's already formed. You don't have to change anything to form it. So we have no enthalpy change that occurs. Remember, enthalpy change is actually final minus initial, right? So if your final and your initial are the same, then your change is 0. So any element you don't actually have to look up because the enthalpy of formation, the standard enthalpy of formation for any element will just be 0. Okay, that's actually thing number 1 I want you to be careful of. Pay attention to the subscripts. Write out your own reactions if you need to, if they're not already given to you. The other things we've actually already talked about, let's just kind of review how enthalpy works. Remember, if the reaction is reversed, the sign of delta H is going to be reversed also. And you can see that here. The only difference between the top reaction and the bottom reaction is that they're flipped. And so the magnitude of delta H is the same, but the sign is opposite. Last note I want you to keep in mind is that the magnitude of delta H is dependent on the quantities of the reaction. So if you have to double a reaction, here's your reaction again, xenon reacting with fluorine, okay, which gives you a delta H of negative 251 kilojoules. If you have to double that reaction, so 2 xenons plus 4 fluorines goes to 2 xenon tetrafluorides, okay, the delta H of that will be doubled also. Okay, so remember, if you reverse it, you have to flip the sign. If you double it or triple it or quadruple it, the reaction, you have to double, triple, or quadruple the delta H as well. Okay, so with that information in mind, I want you to explore this a little bit. So I'm going to post a couple activities for you to do to engage with these ideas. Push your mind a little bit. If you get stuck, bring me a question. The keys are posted. Remember, the keys are posted under our resources on our Google Classroom. So go look at the keys to verify your answers and make sure you are on the right track. Okay, see you in class.